So we're looking at integral calculus now. So we've done differential calculus, which is all about slopes, slopes of lines. We're now looking at integral calculus, which pretty broadly talks about the area under a curve. So an example question we've got here is, consider this function y equals x squared plus 1. How can we estimate the area enclosed by x equals 1? So I'm going to draw on both of these. So this is x equals 1. X equals 1, and it might be a bit confusing while I'm drawing on both at the same time. X equals 4. So I'm going to draw on x equals 4. Nice straight line. And x equals 4 here. Oh, let's just quickly get that up. Okay, and then the x-axis. So we're looking at the x-axis being another boundary here. Okay, and the function. Now, looking at these areas, the easiest and sort of simplest way for us to consider these is fill these with the simplest shape we know, which is rectangles. So if we were going to consider an underestimate, we would draw these rectangles and we would consider, I'm just going to pick 3 because it's a nice interval. If I go at 2 and 3, I break this into 3 equal sections. So I'm just going to draw these lines up. I can make these into rectangles quite easily and use these to calculate an underestimate of the area. So the reason I'm saying an underestimate is because this bit's missed in the area, this bit here would be missed in the area, and this bit here would be missed in the area. So we would be under by a certain amount. Now, you'll notice here that each of my rectangles here, I've picked quite strategically, is 1 unit apart. So if I'm going to calculate these, I will be calculating 1 times something plus 1 times something plus 1 times something. Okay? Now, this function here, x squared plus 1, if I'm calculating how tall this rectangle is here, this value here is going to be f of 1, which means I'm not going to do the working on all of these, but it would mean 1 squared plus 1, which equals 2. So our first one here is 2. So we've got 1 times 2. This next one here of f of 2 is going to be 2 squared, which equals 4 plus 1, which equals 5. So we've got this length here is 5. So I've got 1 times 5. And then this next one here is going to be f of 3 equals 3 squared is 9 plus 1 is 10. So we're looking at 10 here being that. So we've got this area here, which 1 times 2, 1 times 5, and 1 times 10 is going to equal 2 plus 5 plus 10, which is going to be 17 units. Okay, now I'm actually going to just mention, I'll finish the overestimate first and then I'll come back to sum notation. So that's our underestimate, 17 units. And then we're going to consider our overestimate, which is if we could have actually still broken this into the rectangles that we were doing before, but this time we're going to consider going, well, hang on a sec, why don't I do an overestimate here? So I've got this big rectangle here, and then I could have come out and done this value here, and then this here as well. So these would still have 1 unit width. So these would still be 1, 1 wide, and 1. And I've picked these because it's nice and simple doing these. This value here would be the height of this rectangle here is going to be f of 2, so it's at x equals 2, and that's 2 squared plus 1 equals 5. So we're going to have our first rectangle here is going to be 1 times 5. This next one here, this coordinate here will be f of 3, which equals 10. Gives us that value there. So this rectangle here has a height of 10. And then this last one here is going to be given by f of 4, which equals 4 squared is 16 plus 1 is 17. So we've got a height of 17. Oh, that's not a good line. So we've got 17, so plus 1 times 10 and plus 1 times 17. Now, if we think about this, this bit now is an overestimate. We're calculating this area and it doesn't actually exist in the curve there. So we're now going to, we calculate this, we get 1 times 5 plus 1 times 10 plus 1 times 17. It's going to be 32 units squared. And so we know the actual area we're looking for is somewhere between 17 and 32. Now, it's common to actually, let me stop for a minute. I was about to start explaining that, well, this is quite a big gap here. We could probably break one of these into smaller rectangles and it would give us a better estimate. So if we were to consider this, let me just copy and paste this. I'll move this below. Just so we can talk about it, copy. I'm going to have to go at the bottom. So we've got this here. We're going to go better estimate. So if we wanted a less area left out of the underestimate, we could actually break these rectangles and I could do twice as many rectangles and make them smaller rectangles. So here, instead of doing 1, we would have these widths here would actually be a half and a half. So our first unit here would be a half times 2, plus the next one would be a half times, what's this value here going to be? So 3 on 2 squared. So this would be f of 3 on 2. And we'd have to keep going this way. And you'll do these in questions, but I'm just sort of explaining that if you look at just look at this diagram here, all of a sudden, instead of having these big bits that were left out of the estimate, we get this smaller bit here. Now, the reason I'm rushing over this a little bit is because the concept is we can estimate with rectangles. Now, back in the day, before the graphics calculators were as good, we would have had to have set this up as a sum. So we would have gone, well, a sum of our width. So our width here is a half. And we can do these, our width isn't a half, our width is 1. So we would have multiplied our sum by 1 and we got our heights here from our function, which if we're using our graphics calculator, we would have said y1 and put in our values of our first one here, if we're doing an underestimate, would have been x equals 1 and we would have gone up to 3. And it's worth practicing putting that in your calculator. If you put this graph in y1, that would give you the value, and similar to this estimate here would be sum of x equals 2 up to 4, because you'll notice our first coordinate here that we picked up was x equals 2, so that gives us the 2 on the bottom, and our highest one we went up to 4. Now, we're a bit lucky that we don't actually have to do that, and so what we would do here to calculate this area, and this is where that program I've put on your calculators, or if you don't have it, you need to come see me. The program called int_area actually lets us do this. So make sure you have your graph in y1. So your y1 in your graphics calculator should be x squared plus 1. And then what we do is we open the program. And so you go into your graphics calculator. On the menu, you select program. And then select int_area. And then the next step, I've selected it, it comes up with lower bound. Now, the lower bound for this, lower bound is the x value that cuts us in. So our lower bound here, I'll do this in yellow, is 2. Okay, so on both, isn't 2, sorry, it's 1. So our lower bound is equal to 1. This means x equals 1. So we're just going to type 1 in there. The upper bound, which let's change our highlighter to a different color. Let's pick this dark green, is 4. So this is this value here. So upper bound equals 4, which means x equals 4. Okay, and it then says intervals. And as you can see here, I'll just pick this one here. We have 1, 2, 3 intervals. 1, 2, 3 intervals is what we've picked. So our intervals here equals 3. And so we type 3 in, and then when we execute, it pulls up the graph and it shows us those rectangles. So it says left sum, I'm running out of room here. Oh no, I'm not. Left, let's zoom in a touch. Left sum equals 17, which is crazy because that's exactly what we've got there. So then we press execute and it comes up with right sum and starts doing the rectangles, and it comes up with 32. So let's check that. Okay, so 32. And then we go into our next one here and we've got, it does a mid value. So it makes the rectangles. This is a better estimate as well. So 23.75. So it does the midpoint one. And then the next one, it does a trapezoid. And that gives us 24.5. And the best estimate here is 24. It says, so it's sort of letting you know that using these shapes, these are the best ways to do it. Now, that's enough for just estimating the area under the curve. I've just quickly got this other thing in here. Some functions areas can be calculated by area formula. So here we've got base times height, and I've missed divided by 2. We can clearly see this shape here is a triangle. Our next one here, we're looking at a trapezoid if we're doing an area here. And so I've got the formula of a trapezoid below, which is area equals a plus b over 2 times height. And then this next one, I've picked a section of a circle, which is pi r squared, and then we times it by the angle here. And these are ways that we can estimate. So this is just the area under the curve, the first step for us. Thanks, guys.